today, we're talking about merging contracts. Merging contracts is something that developers do a lot when they think they're trying to simplify something. But a lot of times problems have inherent complexity. And when you merge a contract, that inherent complexity is still there. All the different, levers and toggles that exist still exist. All that you've really done is blended them all together and made it very hard to see what's what, right? You've hidden the complexity, not actually reduced it. And so we'll talk about some examples of that right here. This applies to all contracts, all interfaces, even the dashboard or the controls in your car, right? Those are human interfaces, and they have the exact same rules when it comes to sort of merging concerns. So you think of like a dashboard where you've got like heating settings and cooling settings, and you've got maybe certain settings that only apply to one or the other, right? But they're all there merged on your dashboard, intermingled with one another, and it's not readily apparent that one control is only applicable when another control is set to a specific value. And so good interfaces will find a way to sort of like indicate that this control cannot be activated or is not relevant unless another control is present. We'll talk about methods right here. So we're going to talk about this first method here. We've got basically what in methods, the way that this sort of looks is kind of what we would call behavior modifiers. And if you think about that, what are you doing? You're modifying the behavior of a function. A function is a behavior, and you are modifying the function of the function. In other words, you're creating virtual functions within a function. You're hiding functions from the compiler, right? And you've kind of created your own little mini compiler. You've created your own little way of declaring functions, right? That is virtualized above the underlying SDK and runtime that you're actually operating in, right? And why? You know what I mean? Because you're also making it harder for developers to see. So that's what you're doing here. When you've got a method that has sort of like a behavior modifier, right? And we're saying that favorite color, and then we've got this like secret method selector, and based on whether that's true or false, we're going to do completely different things, right? Now that may be because I've got a polymorphic object that I'm passing in here, and in which case it makes sense to do sort of conceptually the same thing, but a little bit different. But still, you want to make that polymorphism declarative, right? So what you would instead want to do is just pass in a polymorphic type, right? Something like that. And then you can use like a visitor pattern to basically apply, to declare to the compiler that the branches are because of polymorphic types, but not because of different functionality. And that is important. That makes it easier to understand that the code changes, why the code changes exist. It's not functional branching. It's type-based branching, right? It's sort of tailored handling with the same conceptual logic. So you can see here, you end up with conditional blocks like this. And importantly, if you're not declaring your polymorphism, then if I call downstream, if I pass, the inputs downstream, what I'm going to end up doing a lot of times is replicating these conditional blocks throughout the stack of my application. And then your cyclomatic complexity goes through the roof, right? And your copy and paste, your boilerplate all goes through the roof. And so what you want to do is instead of having like a behavior modifier that changes what the function does, right? You have two functions, right? And if you need those to be based off of type, then you use a visitor pattern or something like that. But this is clearer. It reduces your code complexity. It's better to have two methods that do two things than one method. This, to a lot of developers, looks like a simplification because you've reduced the number of declared methods, but you still have two methods. You just have hidden one of them, right? You've now hidden both of them, frankly. That is the example for methods. It applies to types. Another type of contract is the actual data that's being passed through, right? So you have in this case, we've got something that's a polymorphic type union. It can be a shape or a color, right? Now you can merge the contracts, and the way this sort of looks, the red flag that you want to look for in data modeling is when you have conditional relevance. So here, you look for behavior modification. Like the purpose of this field is to modify the behavior of this field, of this function. And actually, conditional relevance is still true here. I could have other variables here, right? Where this X is only applicable when that is set to true, right? So you're still going to want to look for conditional relevance in functions also. But in fact, that's just true across the board. Conditional relevance or conditional requirement is an indication that contracts have been merged, which means that it's an opaque contract. So if you want to write good contracts, you want to write good code, probably the biggest, most important thing you can ever learn in your entire career, I would say this is more important than anything else in programming. Period. right? Conditional relevance. If you see conditional relevance in a contract, method, protocol, API, right? User interface. If you see conditional relevance, then you have merged things. And merging does not make things simpler. If you learn that one thing and you figure out how to avoid that, you'll be a great programmer, right? Of course, people who like to merge things and think that that's simple will think you're a bad programmer, and that can be political, but that's a separate problem. Okay, so the idea here is that we've got like sort of undeclared polymorphism. So we've got a shape or a color, but it's all merged together. We've got a shape definition, a shape name that are only relevant if the shape or color type is shape. And color is only relevant. So as a result, I can't actually declare these as required, even though that some of these are required in some cases and others are required in other cases. So my compiler can no longer help me here. I can't use my type safe system here anymore because I've merged everything. And so I can't properly declare the requirements here in a way where the compiler can protect me. And so if I have this method processing the merged polymorphic, right, then I have to do runtime assertions. You know, the problem here again being sort of similar to what we talked about in our last episode on types. If I'm doing a runtime assertion and then I change sort of the requirement of something, you know, if I change this from optional to required, there's nothing that shows me where I've broken something because it's declared optional everywhere, right? So if it now becomes required, there's nowhere for me to, I have to go find every place that's used and inspect it and determine whether or not I've done things correctly, and I could miss something, right? And it also takes time. So it's costing me time. It's making my code harder to read because I've got conditional blocks. I've got runtime checks that the compiler should be doing for me. I'm writing extra code. And if I miss that code, then I possibly got bugs. Basically, the way that you want to do this is with declared polymorphism. Basically, what declared polymorphism looks like is that we actually want to say that we've got two different contracts. Again, same thing with the methods. You're actually going to separate things properly. You can declare that they're part of sort of a conceptual type union, that conceptually they serve the same purpose, but they are separate. They are separate in terms of they're different. I don't know. Anyway, so yeah, you've got your favorite color, your favorite shape, and then you can create a type union. Now there's a kind of a interesting way you can do this. I prefer to use interfaces to declare type unions, but one interesting benefit that you can get in TypeScript from declaring things this way is that it can automatically do your type inference for you in a switch statement. So for example, if shape or color is shape, I no longer need to assert that shape definition exists. See up here, the reason I had to do that runtime assert is because if I don't do that, even though I know that I've got a shape here, the compiler doesn't know that shape definition is always going to be there. And it can't know that because it hasn't actually enforced it upstream through all the calling code. So I have to do that runtime assertion, and I have to do this. It's not just to make the compiler happy. Like I should do this so that I get a friendly error message because I haven't enforced this at compile time. It's possible that the calling code made an error. Whereas if I do this in a type safe way, I can trust that the calling code did not make that error, unless I've come from outside the process boundaries. But that's a separate thing. You want to make sure that when you come in from your process boundaries, you do all the validation necessary to get into a type safe form, right? But everything inside of that, I can trust that it has provided this value if it was able to call this method successfully. So I don't need this. The compiler is going to do it for me. But because I can't be type safe, because I've got a merged contract, I've got to add that code. And now the compiler knows, okay, I can dereference that because I know that it's going to be present at this point. So here I can write less code, right? Now, yeah, I am writing more code here in terms of interface declaration, but everywhere that I use these models will then benefit from that, right? So in here, I'm only using it one time. So yeah, the net cost is probably more code in this particular case, but it's saving me. As soon as you scale this up, it's saving you in bugs and it's saving you in maintenance cost, right? And it just makes it clear and easier to read, right? Like these are the fields that are required for a shape. These are the fields that are required for a color. If I look at this contract here, I have to go one by one and try and figure out shape name. Okay, hopefully it was named correctly, named in a way that sort of like gives me a hint, shape. Oh, that probably only applies to a shape. Probably, right? But there may be times where that's more ambiguous. And I actually have to look at the implementations where this is used to actually understand whether or not shape name is relevant, right? So here, it's a glance. Like that is only relevant for shape. I don't have to look at any implementation. That goes back to our lesson on types. Not burying your contract in implementation saves you time, saves the future developer time, saves the future developer time, and it saves future you time. And that matters. It matters a lot in terms of maintaining the ability cost and scaling your platform, your business platform, right? If you write code that's faster to write for you in the now, it will always be more expensive for the you in the future. And the you in the future does matter, especially as you are building on new features or changing your platform over time, right? So it matters more than the now version of you. You know what I mean? There's a saying in driving. I just got a stick shift car. You know, I haven't had one for like 20 years, so I'm like trying to learn how to redrive it. And there's that old saying, right? Slow is smooth and smooth is fast. Same thing applies to software, right? And a lot of business-oriented like business owners don't get that necessarily, right? Which is that if you push the software too fast, you'll get broken software that has to be constantly maintained and fixed, and it's causing bugs in production and causing your customers to churn, stuff like that. It'll cost you more money in the long run, right? Slow is smooth. Smooth business operations is fast. Right? So that's what we want to talk about here, is doing things correctly, even if there's a little bit more expense in the first use case, so that it stacks returns over time. And I think there's a bit of a myth to that in terms of how much upfront cost there actually is. A lot of times it's actually faster to do it right the first time, right? Anyway, so yeah, applies to types as well. So again, same thing here. We now have our compile time insertions. It's very easy to see at a glance what's required when. I'm not trying to parse contract out of the code. So again, this applies to everything. User interfaces, command line interfaces, Swagger API definitions, GraphQL API definitions, database schema, protocol definitions, standards, specifications, right? Again, physical interfaces in the world, like physical buttons that you push, right? Conditional relevance is everything. This freaking keyboard, right? I love this keyboard, but the point that I'm trying to make is like the keyboard in general. There is so much stuff in here that is conditionally relevant, right? You know what I mean? And I have to process all of that at all times. That's probably not the best example because I don't know how I don't know how I'd fix this. The point is that it applies to physical interfaces. Sometimes in the physical world, you're limited. It's like you can't change this interface so that it shows me different buttons in different contexts, right? I would say though, in the physical world, probably more often than we realize, it is possible to reduce the amount of inputs or contextualize them in a way so that it highlights. For example, even on this keyboard, I could potentially have like some sort of like visual indication of buttons that are relevant in like a typing context versus like a scrolling context versus something else. You know what I mean? And this isn't like the best example. But there are ways to sort of like visually segment things, even if they've got to be on the same sort of visual interface. It'll help cognitively with parsing. This goes in this context, this other thing goes in that other context, and it makes your interface easier to learn. That applies to car makers. If you're watching this, if you make car like interfaces, physical interfaces, which by the way, make physical interfaces. Like Steve Jobs has this thing where he like get rid of everything. There is an extreme that way that you can go too far, and I think that we've gone that way as a society. There is something about being able to not have to look at something to change it, and that usually requires a physical control, right? So anyway, rant over. Conditional relevance is a red flag in your code. This is probably the most important video I'll ever make. It's one of my biggest, most significant, most important learnings that I've ever had in my career is the importance of declaring contracts correctly and the significance of conditional relevance as an anti-pattern, right? Like how bad that is, right? I think that understanding that fundamentally makes the difference between like an advanced programmer and a beginning like nothing else. If you understand that intuitively, night and day, right? Difference in how you approach code and how your code scales. So anyway, that's it. Peace.